Hello everyone, I'm Shiraz Ahmed, and first of all I would like to thank the EurasianSciEnTech 2024 for giving us the opportunity to present a research paper on the topic a review on physical and microstructural properties of fiber reinforced geopolymers. Here is a brief introduction of our authors. First of all, I would like to explain the abstract of the paper to all of you. The use of fly ash and the slag in geopolymer composites can worsen the weakness of traditional cement-based composites under tension, potentially leading to the cracking and swelling, which can have financial and safety consequences. The fiber reinforcement has long been used to improve the durability, strength, and flexibility of regular cement concrete. As the world moves away from Portland cement-based products, there is growing interest in adding fiber reinforcement to the geopolymer composites, creating the fiber-reinforced geopolymer composites that serve as eco-friendly alternatives for the structural purposes. However, further research is needed to fully understand their effectiveness across different applications. Nowadays, the geopolymer is gaining interest across the industries for its eco-friendly applications. It's an inorganic material formed by the combining aluminum silicate components with an alkaline solution. Compared to the traditional Portland cement, geopolymer production requires significantly less material and energy, leading to lower carbon dioxide emissions. Studies highlight that the geopolymer's durability, heat, and the early stage strength. Research by Davidovitz explored the fiber modified geopolymer systems, showing that the fibers enhance the toughness, they control the cracking, and they prevent the brittle failure by inhibiting the microcrack propagation. These fibers also reduce the environmental impact compared to the traditional fiber-reinforced concrete. Synthetic, steel, and inorganic fibers in geopolymer reduce the emissions by 19%, 32%, and 37% respectively, according to Abdul Karim et al. Here is the application of various types of fibers in geopolymers. First of all, there are fresh features which include the workability, density, drying shrinkage. Next, we have the mechanical features. They include compressive strength, elastic modulus, tensile strength, flexural strength, and the load deflection behavior. Next, we have the durability features. They include the porosity, chemical acid attack, and chloride penetration. And among the characterization, we have X-ray diffraction, scanning electron microscopy, and thermogravimetric analysis. Next, over here we will discuss the effects of various types of fibers. First of all, we will discuss the compression strength among the mechanical properties. Compression forces induce microcracking and fractures in brittle materials, affecting the compression response. Butta et al. Studied the reinforced geopolymer mixes, finding heat curing enhances the strength. The reinforcement improves the compression strength due to its high modulus of elasticity compared to the polypropylene fibers. The silica negatively affects the geopolymer strength, elevated by adding the synthetic fibers. Excessive fiber content decreases the strength by increasing mixed viscosity. And next we have the two graphs. The MSF boosts the early strength but diminishes over time, whereas the PPF reduces the long-term strength with higher concentrations, causing more significant declines, as you can see in the figure given. Next we have the modulus of elasticity. A material's modulus of elasticity indicates the better matrix quality and higher compression strength. A higher modulus typically indicates the better matrix quality. Fiber type, shape, and proportion influence the performance, affecting both the geopolymer modulus and matrix porosity. The larger moduli in plain and fiber reinforced geopolymer correlate with increased compression strength. The figure compares the regression models for high strength concrete with elastic modulus data for plain and fiber reinforced geopolymer. The fiber-reinforced geopolymer shows the trends similar to the Portland cement with convergence in compression strength. The oil palm shell fiber lightweight concrete with geopolymer mortar compares favorably due to the concrete's heterogeneous nature. Notably, the plain geopolymer modulus remains lower than the fiber-reinforced geopolymer systems under ambient curing, showcasing their distinct performance characteristics. Next, we have the tensile strength among the mechanical properties. Adding 50% recycled aggregate to the strength geopolymer increased tensile strength 0.10 to the 0.30. Weight percentage addition resulted in 8% to 38% higher tensile strength than control specimens. The 6 millimeter reinforced geopolymer with 0.1% weightage percent fibers increased the tensile strength by 55%. Excessive fiber length can reduce the tensile strength. Ideal lengths maximize the benefits. That was quoted by the Wang et al. The 3 to 6 millimeter fiber length increases the improved tensile strength by 8%, but strength declined by 12% with longer fibers due to aggregation issues. Next, we have the flexural strength. The flexural testing assesses the tensile strength of geopolymer samples by evaluating beam specimens under 3 or 4 point stresses. Guo and Penn found that Increasing synthetic basalt and polypropylene fiber concentrations from 0.1% volume to the 0.3% volume reduced the composite flexural strength. However, the strength increased when fiber content was raised to 0.5% of the volume, with 0.5 volume percentage producing the best results. Synthetic fibers notably strengthened the geopolymer composites, showing a 21.5% increase over reference specimens due to their high modulus of elasticity, enhancing the resistance and stress distribution, as you can see in the figures. Next, we have the load versus deflection behavior. The load bearing capacity of the fiber reinforced geopolymer composites increases significantly after initial breaking but before failure due to the high tensile strength and robust connections at the hooked ends of the fibers. Finite element study by the Sanjayan et al. Showed enhanced toughness with increased fiber content, with highest fracture toughness at 5 volume percentage fiber addition through experimental data indicated 3 volume percentage as the highest value. Gu and Pan found that 0.3% volume percent basalt fiber reinforcement in geopolymer composites resulted in 32% higher deflection and 45% higher loading compared to the unreinforced composites, with negative impacts observed at fiber contents exceeding the 0.4 of the volume percentage. The Natali et al.'s study showed that the synthetic fibers, which include carbon, glass, and polyvinyl chloride at 1 weight percentage and 7 mm length, improved geopolymer composites energy absorption capacity and post-cracking responses more effectively than the inorganic fibers, as you can see in the figure. Next, we have the microstructural properties. We will discuss them, and first of all we will discuss the scanning electron microscopy. The interfacial transition zone initiates the chemical bonding during the fiber pullout, enhancing the matrix fiber interaction. ITZ performance is influenced by the solution to binder ratio, additives, and binder properties. Larger fiber aspect ratios compared to the aggregate aspect ratios increase the contact surface area. The superior fiber matrix bonding in fiber reinforced geopolymer results in better performance and consistency around the fibers during the hardness and the shrinkage, as you can see in these figures here. Next, we have the X-ray diffraction. Using X-ray diffraction, the Renschmar et al. Found the sourced mullite phases on the unreinforced paste geopolymer in addition to the crystalline phases of the quartz. The XRD, which stands for the X-ray diffraction, peaks for the fiber reinforced geopolymer resembles those of plain composites, indicating the minimal fiber impact on geopolymerization. The mineral phases in both plain and the synthetic fiber reinforced geopolymers were comparable. Next, we have the challenges and the further recommendations relating to our research. There are differences in the composition and quality of the components of geopolymer composites. It may get more complicated to incorporate the slag and other components like metacholine. Therefore, a thorough database is required to include these precursors and fiber materials in a definite manner. For fiber strength cement concrete, there are a number of different fiber pre-treatment techniques that can be used, such as laser treatment, flame surface oxidation, surfactant modification, cement lime pre-coating, and many more. For natural fibers, however, additional evaluations are needed in a variety of geopolymer system compositions. There hasn't been enough research done on the different characteristics of metacholine and the geopolymers with other fiber strengthening, so more research is advised here. Next, we have the conclusion. In the fiber reinforced geopolymer systems, it was discovered that the fibers with a higher aspect ratio were more prone to the belling and breakage, which decreased the corresponding strength of the composites under compression. Fiber percentage significantly affects the mechanical properties, with short fibers controlling the microcracking and long fibers enhancing the final strength and preventing macrocracking. The fiber volume percentage and specific gravity impact the fiber reinforced geopolymer density. Adding fiber reduces the drying shrinkage in geopolymer composites, with fiber characteristics influencing the composite reaction. Fibers control the cracking while creating airwards, affecting compression strength. Fibers enhance the flexural and tensile strength, with fiber properties impacting geopolymer strength. The optimal fiber percentage for the synthetic fiber reinforced geopolymer is around 0.75 volume percentage. The fiber characteristics influence the fiber reinforced geopolymer morphology, with the ITZ playing a crucial role in the mechanical properties. Adding the GGBFs improves the fiber geopolymer base bond strength, and the proper preparation of the fiber enhances the bonding with the matrix, contributing the positivity to the fiber reinforced geopolymer system's response. The shape, the concentration, the size, and the kind of fibers have a significant impact on the morphology of the fiber reinforced geopolymer, as discussed earlier. So, compared to the regular geopolymer, the ITZ has the greater influence on the mechanical characteristics on the of the fiber reinforced geopolymer systems. Thank you for listening, everyone. Once again, thanks to the EurTech, EurasianSciEnTech 2024.